Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for trapping rainwater problem. Let's look at the problem description. We are given n non-negative integers representing an elevation map where the width of each bar is 1. And we have to compute how much water it can trap after raining. Let's take a look at the example 1. So we are given the elevation map as an array of integers where each integer is the height of that bar and each bar is of width 1. Okay, so in this case we can trap here 1 unit and here 1 unit, here 1 unit, 1, 1 total so far 5 and plus 1. Okay, 6 units of water we can trap in this. So we have to return 6. The constraints for this problem are n is equal to the length of the height array, and where n is ranging from 1 to 20,000. The value of the each element in the array is ranging from 0 to 100,000. Let's look at the approach to solve this problem. We are given this input height array, and each entry in that array indicates the height of the bar. Okay, so the expected output is 6 because the elevation map shows that the water can be trapped here and here 4 units, here 1 unit. So totally 6 units of water can be trapped in this. So that's why the expected output is 6. In order to derive the algorithm to compute the amount of trapped water, first let's take a look at the few simple cases. So in case 1, the left end of the map have a bar of height 2 and the right end is of height 3. So in this we can collect the water up to height 2. If we fill up to 3, it will overflow, right? So the height of the trapped water is always equal to the shortest side of the collection window. Okay. In case 2, the first bar size is 3 and the last bar size is 1. In this case also, the trapped water height is equal to the shortest side of the window. So it is equal to 1. So from these two cases, what we can conclude is always try to process the shorter side of the window. Okay, so in this case we start processing from this side, the left side, and in this case we start processing from the right side. In case 3, the first bar is of size 3 and the bar at index 4 is of size 2. The trapped water in this portion is of height 2 and the other side the trapped water height is 1, right? If we always process from the shorter side, we can easily compute the trapped water. So if we keep computing from this side, it is easy to calculate. So basically we can solve this problem using a 2-pointer approach. We can position the pointer at the first index and the last index of the given array. Okay, and we always try to process from the shorter side. Okay, in addition to the pointers, we also have to keep track of the maximum height we see from that side. Basically we have to maintain a max left height that keep track of the tallest bar we have seen so far when we move the left pointer from this side to this side, and we maintain another variable right max height that keeps track of the tallest bar we have seen so far when we process from the right side. So we keep updating whenever we see the current bar height is greater than the max height, then we update the max height. Otherwise we subtract the current index value from the maximum height we have seen so far and add it to the trap count. For example, in this case left pointer starts from index 0, the right pointer start from index 8. Okay, so each time we compare which bar is a shorter one. So in this case the right side bar is shorter one, so we process from the right side. We process the right side. First we check whether the current bar height is greater than or equal to the maximum height we have seen so far. If it is less, then we subtract the current value from the maximum bar height. Okay, for example, in the first iteration we see this bar of size 1, so we update the maximum height of the right side thing to 1, and the rest of the 3 entries have a 0 value in the array. Okay, so because that is less than the max height seen, we subtract this value 0 from the max height, which is 1. So 1 minus 0, 1. For this iteration we add 1 to the trapped count, and when we come here again this value is 0 than less than the maximum height we have seen so far, and when we come here again 0, so that is less than the maximum height we have seen so far. So in each iteration we add maximum height minus the current value 0, 1, 1, 1. So we add 3. Okay, and then when we reach this point we see the current element height is greater than the maximum height we have seen so far. In this case we simply update the maximum height to 2. Okay, and we move on to processing the next, and we compare whether this height is greater than this height. It is not, so we start processing from this side, so we simply advance the right pointer, and when we come here we see 0, which is less than the current maximum height, which is 2. So 2 minus 0, 2. So we add 2 to the trapped count. So now it will become 5. So likewise we keep adding. When we reach here 6 units is added from this part of the elevation map, and 3 will be added from this part of the elevation map. Totally we get 9 units of water in this case. Basically we can use the 2-pointer approach to solve this problem, and we maintain the left pointer and the right pointer. We keep checking the height of that particular entries, and whichever is less we start processing that side, and we always keep remembering what is the maximum height we have seen so far from that side, whether it is a left or right. We keep track of the maximum height, and if the current element height is less than the maximum height we have seen so far, we compute the difference and add it to the trapped count. Okay, so that's what I have listed here. We position the left pointer at index 0 and the right pointer at index 11, the last element. Okay, and then we initialize the trapped variable to 0 and the left max height to 0 and right max height to 0. Okay, and then then we process the entire array until both the left and right pointer meets. Okay, so in each iteration we compare the element pointed by the left and the right pointer. If the entry is pointed by the left pointer is less than the entry pointed by the right pointer, then we process entry pointed by the left pointer. Okay, and we compare that value with the left max height. If that is greater than left max height, then we update the left max height. Basically we keep track of what is the maximum height we have seen so far on the left side. Otherwise we compute the difference between the left max height and the current entry and add it to the trapped variable. Then we advance the left pointer. So this processing is done when the height of the left element is less than the height of the element pointed by the right pointer. Otherwise we process the element pointed by the right pointer. So in this case we compare the value pointed by the right pointer is greater than or equal to the right max height. If so, update the right max height. Otherwise compute the difference between the right max height and the current element and add it to the trapped variable and decrement the right pointer. We repeat that process until the left and right pointer meets. Finally, the trapped variable contains the amount of water that can be trapped in this elevation. Let's look at the flowchart. Input for this procedure is an array of integer height. And first we initialize the left and right indexes. The left is initialized with the value 0, the first element in the array, and the right pointer is initialized with the last element, which is the length of height minus 1. And then we initialize the left max height to 0 and right max height to 0 and the trapped count to 0. Okay. Then we enter the loop. There we check whether the left pointer is less than the right pointer. In that case, we have still element to process, so we enter the for loop body. And there we check the element pointed by the left pointer is less than the element pointed by the right pointer in the array. In that case, we process the element present in the left side of the window. Okay. So there we check whether the element pointed by the left pointer is greater than the left max height. If so, we update the left max height with the current value. Otherwise, we compute the difference between the left max height and the element pointed by the left pointer and add that difference to the trapped variable. Then we increment the left pointer so that the next element will be processed in the next iteration. So if the element pointed by the left pointer is greater than the element pointed by the right pointer, then we process the element present in the right side of the window. There we check whether that current element is greater than the right max height. If so, we update the right max height. Otherwise, compute the difference between the right max height and the element pointed by the right pointer and add that difference to the trapped variable. Once that is done, then we have to advance the right pointer, so we decrement. So we repeat this process until the left and right pointer meets. Okay. So once the left and right pointer meets, then we come out of the loop and we return the trapped count. Let's move on to coding. First I initialize the left pointer to 0 to point to the first element in the array and the right pointer to the length of height minus 1 points to the last element of the array. Then I initialize the left max height to 0 and the right max height to 0. And the trapped count to 0. Next I write the for loop. This runs until the left and right pointer meets. Each iteration I compare the value pointed by the left pointer and the value pointed by the right pointer. And whichever is smaller, I process that side. So in the case the left side is smaller, then I check whether the value pointed by the left pointer is greater than or equal to the left max height. If so, update the left max height. Basically, we keep track of the maximum height we have seen so far from the left side. Otherwise, I subtract the value pointed by the left pointer from the left max height and add it to the trapped count. Then I increment the left pointer. If the element pointed by the right pointer is smaller, then I process the right side. In that case, I check whether the element pointed by the right pointer is greater than or equal to the right max height, then I update the right max height. Else I compute the difference and add it to the trapped count. Then I decrement the right pointer, and finally I return the trapped count. Next I am going to run the test cases. All the tests passed. Next I am going to submit this program. Cool, this program is accepted. Next I am going to do the code walkthrough with sample input. Let's do the code walkthrough for this input, and the expected output is 6. We can trap 6 units of water. Okay. First we initialize the left pointer and the right pointer. Left is initialized with 0 and the right is initialized with index 11. Next the left max height is initialized with 0 and the right max height is initialized with 0 and the trapped count is initialized with 0. Then we enter the for loop. We check whether the left pointer is less than the right. So in this case it is true. So we enter the body, and there we check the element pointed by the left pointer is less than the element pointed by the right. So in this case it is true. So 0 is less than 1. So what we do, we check whether the element pointed by the left pointer is greater than or equal to left max height. So it is 0, that is greater than or equal to the left max height. So we update the left max height with the value 0, and then we increment the left pointer. So now when we leave the iteration 0, the left pointer is advanced and pointing to the element at index 1. So when we leave, it is 1, from 0 to 1. And in iteration 1, we compare the value pointed by the left and right pointer. So both are equal. So in that case we process the right side element. Okay. So there we check the element pointed by the right pointer is greater than or equal to the right max height. So in this case it is 1, that is greater than the right max height 0. So we update the right max height variable to 1. So it points to the maximum height we see so far in the right side. And in the iteration 2, again we compare the element pointed by the left and the right. Okay, so in this case the left pointer points to the value 1 and the right pointer points to value 2. Left side is smaller, so we process the left side. So there we check current element pointed by the left is greater than or equal to the left max height. So this is 1. So left max height is 0. So we update the left max height to 1. Okay. And then we advance the left pointer. So the left pointer is set to 2. Now pointing to the element at index 2. And in the iteration 3, we compare these two values. So this value is smaller, the left side is smaller than the right side. So we process this element. So in this case we compare the element pointed by the left is greater than or equal to the left max height. In this case it is not. So it is 0 and the left max height is 1. So we come to the else part. There we compute the difference between the left max height and the element pointed by the left pointer. So 1 minus 0, that value will be added to the trapped count. So we get the trapped count value set to 1, and then we advance the left pointer. So now the left pointer point to index 3. In the iteration 4, we compare the value again. So both are equal. So if it is equal, then we do process the right side. We compare the value pointed by the right pointer with the right max value. So the right pointer, so this value is 2, which is greater than the right max value. So we simply update the right max value and advance the right pointer. So that's why we see the right max height becomes 2 and the right pointer is decremented, so it points to 9. And in the iteration 5, we compare these two values. So again, the right side is smaller, so we process this side and we compare this value with the right max. So the right max is greater than the current value. So we simply compute the difference between these two elements. So the difference is 1 and that gets added to the trapped count. So we get trapped count 2. And in iteration 6, we see both the elements values are equal. So in that case, we process the right side and we compare this value with the right max. They are equal. So we simply update the right max again and advance the right pointer. So that's why we see the point when we leave iteration 6, the right pointer points to element at index 7. And in iteration 7, we compare these two values. So now the left side is shorter. Then we compare this value with the current left max height. Then we see this is greater than the current left max height. So we simply update the left max height and I increment the left pointer. So now the left pointer points to 4 and the left max height is updated to 2 from 1. And in the iteration 8, we compare these two values. Again, the left side is smaller. So and then we pick up that value and compare it with the left max height. So the current value is lesser than the left max height. So we compute the difference 2 minus 1 and that value will be added to trapped count. So the trapped count becomes 3 in the iteration 8. And we advance the pointer. Now the left pointer points to 5. And in the iteration 9, we compare these two values. Again, this the left side is smaller than the value pointed by the right pointer. So we check this value with the left max height and this value is smaller than the left max height. So we compute the difference 2 minus 0. That value will be added to the trapped count. So we see the trapped count is updated to 5 and we advance the left pointer. So now the left pointer points to index 6. Then in the iteration 10, we compare the value pointed by these two values. Again, the left side is smaller. So we compare this value 1 with the left max height. So we subtract that value from the left max height. Then we get 1 and that gets added to the trapped count. So the trapped count becomes 6 and we advance the left pointer. So the left pointer now points to 7 and now the left pointer points to index 7 and the right pointer is also pointing to index 7. So because both are meeting, we come out of this for loop and return the trapped. So the trapped count is 6 and that is an expected output. Next I am going to do the time and space complexity analysis for this solution. Let's do the time complexity analysis for this input. Let's see how many iterations this for loop performs in order to compute the output 6. Okay. So as per the code walkthrough section, it performs 11 iterations. So for the size of this input array is 12. So for the array with size 12, we have to perform 11 iterations. So the array of size n, then we have to perform n minus 1 iterations. So the time complexity is order of n. And with respect to the space complexity, it is order of 1 because we are not allocating any additional space in this procedure to store the intermediate output. We just use few variables. Okay. So the space complexity is order of 1. Thanks for watching this video. Have a great day.